Imagine trying to teach a computer to see and understand images like we do. It's a challenging task. Convolutional neural networks, or CNNs, are a special type of artificial intelligence that excels in this area. They are like our brains, learning to recognize patterns and objects within images. CNNs power many of the image-based applications we use daily. Think about facial recognition on your phone or how self-driving cars see the road. These technologies heavily rely on CNNs to make sense of visual information. The power of CNNs lies in their ability to learn hierarchical representations of images. They break down images into smaller, more manageable pieces, extracting meaningful features at each step. This process allows them to identify complex patterns in objects regardless of their position or scale within an image. In essence, CNNs are like skilled detectives meticulously analyzing every detail of an image to understand its contents. They have revolutionized the field of computer vision, enabling machines to see and interpret the world around them with remarkable accuracy. At the heart of every CNN lie convolutional layers, the workhorses responsible for extracting features from images. Think of these layers as detectives using magnifying glasses to examine every nook and cranny of a crime scene. A convolutional layer scans an image using small filters like sliding windows to detect specific patterns. These filters are like templates, each designed to recognize a particular feature, such as an edge, a corner, or a texture. As the filter moves across the image, it calculates how well the underlying pixels match the template. This process generates a feature map, highlighting the locations and strengths of the detected features. For example, a filter trained to detect edges will produce a map where bright pixels indicate strong edges, while dark pixels represent areas with fewer edges. By using multiple filters, each tuned to different features, convolutional layers build a rich representation of the image, capturing its essential characteristics. These extracted features then serve as building blocks for subsequent layers to further process and analyze. As convolutional layers extract features, they generate a massive amount of data. Pooling layers come into play to simplify this information, reducing its dimensionality while preserving essential features. Imagine looking at a painting from afar. You can still discern the overall composition and key elements without getting bogged down by minute details. Pooling layers achieve a similar effect by downsampling the feature maps. One common type is max pooling, which acts like a sieve, selecting only the most prominent feature within a small region. This process reduces the size of the feature maps, making the network more computationally efficient and less susceptible to overfitting. Pooling layers also introduce a degree of spatial invariance, meaning the network becomes less sensitive to the precise location of features within the image. This property is crucial for recognizing objects regardless of their position or orientation. After the convolutional and pooling layers have extracted and simplified the image's features, the final stage of a CNN involves making sense of this information and producing a classification. This is where fully connected layers come in. Think of these layers as the jury in a courtroom, weighing the evidence presented by the previous layers to reach a verdict. Each neuron in a fully connected layer receives input from all the neurons in the preceding layer, allowing it to consider the entire feature representation. These neurons learn complex relationships between the extracted features, essentially figuring out which combinations are indicative of specific objects or classes. The output of the final, fully connected layer represents the network's prediction, indicating the probability of the input image belonging to each class. For example, in an image classification task, the fully connected layers might determine whether the image contains a cat, a dog, or a bird, based on the features extracted by the convolutional and pooling layers. By combining convolutional layers for feature extraction, pooling layers for dimensionality reduction, and fully connected layers for decision-making, CNNs provide a powerful framework for image classification and other computer vision tasks.